Okay, so we're looking at the second of the videos of kinematics, and this time it's going to be velocity and speed. So velocity and speed aren't the same things, although they are connected in some ways. Okay, so velocity is a vector. It has direction and magnitude. Speed is a scalar. It just has magnitude. So how I could explain it might be you're traveling on Northbourne Avenue and your car is measuring 60 kilometers per hour on Northbourne. And so the speed is 60 kilometers per hour, but the velocity could be 60 kilometers per hour north because you're heading to Sydney. Okay, so they could have the same number, same magnitude, but one has to have a direction. So whenever you have vectors, they have to have direction. Okay, so copy that and come across. So here's some definitions. The average velocity is not the same as the average speed. So the average velocity is the change in position from start to finish over the change in time. But the average speed is the total distance you travel over the change in time. So there's a difference again, speed and velocity by that formula. And just so you understand connection, if you ever get asked the instantaneous speed, well, that's just the gradients at a time. And so it's just the first derivative of the displacements. Okay, so copy that and come across. Okay, just to cover the things, units for speed. So distance is measured as meters or kilometers, and time could be seconds or hours or minutes. So the unit for speed or velocity, now velocity has direction, but we still have to have a unit. So the meters is, so you're traveling at 6 meters per second, so it's written as meters per second, and in some books they might have ms-1 or kmh-1. So meters per second. Okay, just think of, you know, meters per second like that, and then when you bring up s to the top, you change the indices. Okay, let's have the last one. Okay, so we've got now an example. A particle moves in a straight line so that its position x relative to O, which is the central position at time t, is given by blah blah blah. So this is that same formula that we had last time. So here, because the questions end up being velocities and speeds, so they can relate to position and changes in position, so we need to sketch the graph. Okay, so if you want to have a go at it yourself, have a crack, otherwise just wait and come back when you're ready. Okay, so you're back. Okay, so I'm just getting my slides ready. Okay, so factorize, so it's got a plus at the back and a minus in the middle, so it's two minuses. So it's t minus 6, t minus 1, and so at 1 and 6 there's going to be a change, t x, so we're measuring x versus t. It starts at 6. Okay, that's the initial position. It's a parabola because it's a squared, and it's going to come down and go back up. Okay, so at t equals 1 and t equals 6, at t equals 1 and t equals 6, x will be equal to 0. Okay, so that's the first one. Part B, its initial position is 6 meters, and we could say to the right if you wanted to. Part C, find when and where. So when is the time, so t equals 1, t equals 6 is the when, and the where is when you substituted. Hang a sec. So I just made a mistake. I've just checked my notes. So that's not when the particle's at rest. The particle is at, gotta check my notes. The particle is at rest when it's stationary, and it's stationary there. That's where it's not changing position. So it's stationary between 1 and 6. So at rest is between those 2 points. So 6 plus 1 over 2. So it's at rest at 3.5 seconds. So 1 and 6 is when it's at 0. My mistake. So that's when, and where will be the x answer. So x at 3.5 equals 3.5 squared minus 7 times 3.5 plus 6. And according to my calculator, that's at minus 6 1/4. So these are all centimeters. So centimeters. Okay, so find when and where. So I've done that. Okay, part d. Okay, the average velocity equals the change in position over the change in time. So the change in time is going to be 8 seconds. It's only in 4 seconds, sorry, beg your pardon. So in 4 seconds the particle has moved from 6 down to